Thank you for the introduction. Hello, I am Yongchan. Today, I would like to talk about uncertainty quantification using Bayesian neural network in classification and its application to ischemic stroke lesion segmentation. This work is jointly with my Professor Jung-Ho Won and Dr. Bum-Jun Kim and Professor Myung-Cho Park. First, I'd like to start with a recent paper, a survey on deep learning in medical image analysis. Without doubt, there has been a steep growth in medical imaging analysis as technology of deep learning developed. However, I would like to ask one thing. Do we really understand deep learning well? I mean, more precisely, do we really understand the deep neural network model output well? Here, I give a toy example. I trained a simple LEsion with CIFAR10 dataset. So it achieves 95 accuracy on test dataset. It is almost state-of-the-art model. And here's our example. Left side are correctly classified images, and right side are misclassified images. First, in the left side, as you can see, all 4 images are correctly classified and with high probabilities. So, yeah, it did a good job. However, on the right side, it looks weird because on the first image, here, the originally labeled with a bird, but it predicted as a dog with high 0.99 probabilities. Yeah, but birds and dogs are both animals. However, the last images, its true class was the cat, but it predicted as an airplane with 0.88 probabilities. If something weird happened, and this is how a typical neural network do, even it is a state-of-the-art model. So when it comes to the healthcare decision support system, which makes use of neural network model output, yeah, it may cause a severe problem, I think. So understanding model output is so essential. Here I bring 2 detailed regions. First is that absence of sufficient knowledge of model output provide partial information. So in previous example, we only got the point probability, not the interval information. And second is that neural networks are really prone to overfitting. In previous example again, the misclassified images have spuriously high confidence. So how to deal with that? One possible answer is to understand the output via quantifying reliable uncertainties. So to be specific, here in the the box, I will denote y and x are target variable and x is our input variable respectively. And we assume we have a deep neural network fx indexed by parameter theta, and we have at inference we have a new input x star. Then question is, what is the up distribution of y star when using a neural network output y star hat? Or do we have any value that representing the uncertainty of this model output distribution? The science of answering this kind of question is called uncertainty quantification. And for answer this, using a typical neural network may be inappropriate, because to obtain the model output distribution, you may need to train multiple neural network. But yesterday at AIDEN's presentation, I was really shocked that they really did that, and under the name of bootstrapping. It was really great. But today, I will use the Bayesian neural network. Let me briefly introduce the Bayesian neural network. While typical neural network models are deterministic, composite layered function, but under the Bayesian framework, we place a prior distribution on parameter vector. So in the figure, left side image illustrate that a typical neural network, and right side illustrate that Bayesian neural network. So all the biases and weights are represented random distribution. Under this assumption, Bayesian neural network offer probabilistic interpretation via posterior distribution, so which is likelihood times prior over the data distribution, And the predictive distribution follows as integral of likelihood times posterior over the parameter spaces. That is, in short, if once you get the posterior distribution, you can quantify uncertainty via this predictive distribution. Yeah, that's good. But historically, the calculating this part, the PD, is not easy in general because of complexity of neural network. But there have been amazing efforts to resolve it, and there are two practical approaches to running Bayesian neural network. I will not go in details, but first is that Monte Carlo Markov chain based on first or second order of stochastic Langbaum dynamics algorithm. And second is that variational inference, which approximate the true posterior distribution with tractable density functions. So go back to our original question, uncertainty quantification. We will assume that we have a well-trained Bayesian neural network. So it is a story about how to give a good little uncertainty quantification method, not the running process itself or specific data analysis. So here I will denote the P bar is the estimator for expected probabilities, average of likelihood, which is average of likelihood, and omega T hat is randomly sampled from estimated posterior with capital T times. So historically, there have been some uncertainty quantification method for classification. The first is that Gal, in his PhD thesis, introduced the entropy-based uncertainty quantification method. This is given by negative summation of p times log p over the classes, and also suggested plug-in estimator. And yeah, this is very good. And I found that many papers accepted in this MIDL conference used this method. Yeah, so it's very good. However, the Kendall and Gal noticed that note that it only captures the predictive distribution. But I mean, in Bayesian modeling, predictive uncertainty can be divided into two parts. One is aleatoric uncertainty, and the other is epistemic uncertainty with respect to its sources. So aleatoric uncertainty, also known as irreducible uncertainty, captures noise inherent in the observation. So it is about data-driven noises. In contrast, epistemic uncertainty, known as reducible uncertainty, accounts for model uncertainty. So it arises by lack of knowledge of the true model. Kendall and Gal noticed that and introduced the moment-based predictive uncertainty and decompose it as in this equation. When you consider a simple Bayesian linear model, then aleatoric uncertainty is about it measures variance of error term, and epistemic is about the variability of posterior distribution, and more importantly, it converges to zero when the sample size increases, and this property is called posterior consistency. And the same paper, Kendall and Gal used the 2K neurons in the last layer for K-class classification problem and modeled the mu and sigma square, each are K neurons, mu for mean and sigma square for variance of the output spaces. And proposed this kind of uncertainty estimator. And I also found that there is a paper used this method in this MIDL conference. And I think it's really good, but for classification, we need to think more. I mean, when you guess a binary random variable, with a mean p, its variance is p times 1 minus p. That is, there is a functional relationship between the mean and variance, but it ignores it. And second is that aleatoric uncertainty only models a diagonal matrix form. And the third, the worst is that the equation, the models, the uncertainty of linear predictor, I mean the logit space in the logit spaces, not the predictive probability. So it is just uncertainty estimation for intermediate layer output, not the model output. So how to solve this set? We solve all these problems by this equation. So we propose the moment-based uncertainty estimator given by this. Here, the aleatoric is that average of diagonal minus p square, and epistemic is that variance-like estimator for p. When you consider in the binary classification setting, the aleatoric is end up with p times 1 minus p. So it considers the functional relationship between mean and variance of multinomial outcomes. And also, it does not restrict to diagonal matrix modeling, and which gives the more importantly is that it's uncertainty about the predictive model outcome. So I can say it is more natural for classification problem. And it is worth notice that there is a connection between the proposed method and the Gal's entropy-based method. In the figure, the red line is the entropy-based method uncertainty, and the blue line is the trace of aleatoric plus epistemic uncertainty. That is, so in the figure, it is symmetric and it increases up to 0.5 and decreases otherwise. So it preserves the monotonicity, and more importantly, when the expected probability p bar are near 0 or 1, entropy can be approximated by trace of aleatoric plus epistemic by Taylor expansion. So in short, in short, so when you have a set of samples from the posterior distribution, you may get the similar result with the entropy-based method and our proposed method, but our proposed method give additional information which decompose the two uncertainty. For the time limit, I will briefly show my application of ischemic stroke lesion segmentation. One thing I want to say here is that yeah, we need a fast and accurate decision support system. So and Mikai noticed that and annually run the ISLS challenges, ischemic stroke lesion segmentation. And I bring the two data set. One is SISS and the other is SPES. The number of subjects are comparable, but the two main different thing is that total number of boxers, which is the boxers of SISS is much larger than SPS, which affect to the epistemic uncertainty, and the proportion of stroke lesion for the SPS is much larger than the SISS, which will affect the aleatoric uncertainty. Here is a visual comparison of uncertainty quantification method. The P indicate the proposed method, and K indicate that Kendall and Gal method. You can here's a MRI flare images, aleatoric, epistemic, sum of aleatoric plus epistemic, and predictions and ground truths. You can see both are produced a similar result here, but the uncertainty maps are totally different. Actually, the Kendall and Gal method, the variance parts are converged to 0, so it gives less informative images. Here, this area, where the prediction disagree with the ground truth, and in the aleatoric map and the predictive uncertainty map, it shows a higher uncertainty. Here, the light value indicate that higher value. This continues to the SPES data set also. Here, this area is agree with the ground truth, but it shows a higher uncertainty. And here's the quantitative result. In one word, as anticipated, it did it. Here, so conclusion is that understanding uncertainty of predictive outcome is so essential, especially in medical imaging analysis, and we propose a more natural method for classification. Thank you for paying attention.
Perfectly in time. That was an impressive
really?
speed up.
Thank you.
The paper is open for questions. I had one question. So I was a little bit surprised that the Kendall and Gal approach doesn't seem to work at all.
Actually, I think it will work well if I choose the regularized parameter. It is about the regularization parameter problem. You know, I mean, when training the Kendall and Gal method, you need to specify the lambda, the regularization parameter on the Kullbaum-Leibler divergence, and it really depends on the performance.
Okay. So better tuning of the parameter might have helped.
I'm a bit confused. What do you think is a good result in terms of separating epistemic and aleatoric uncertainty? So what would be the perfect prediction in your case here?
Here?
Yeah, so what would you think is the best way to separate these two types of uncertainties?
It's very difficult problem, but I guess that when sample size increases, epistemic uncertainty should go to 0, and only aleatoric remains. But it is, I think, in my experience, it is very difficult to get, because when you use the MCMC method or variational inference method, we have a bias on the true probability. So because due to biases, it's hard to get the ideal results.
Thanks.
Hi, thanks for your presentation. I have a question. Did you look maybe how the epistemic developed during training? So you would expect maybe that it's large in the beginning, and if you see more data, it's reducing?
It's not really, but I think that when you have some decision support system, I think only giving the point prediction is not sufficient, and we need to give all the information to the doctor or someone. So maybe for the model devising, well, maybe I think it will be used, but I'm not sure. But this is for the natural method for uncertainty quantification.
So in the interest of time, okay, one last question.
Hi, thanks. I was wondering, your method, it's used for multi-class classification, right? And you were saying that your method is also good because it kind of decouples the mean and the variance nicely. Yeah. Have you considered the fact that the variance, like the individual elements of the variance, that covariance matrix diagonal, are going to be coupled in a multivariate
that is also a good question, but I have been tried before, because when you consider only the binary classification, it is usually so. And also this figure is that the one term of the elements. So.
Oh, just the trace.
Yeah, just trace. I mean, the trace is the same in the binary classification problem. Just p times 1 minus p, and also p times 1 minus p.
Maybe we'll take this offline.
Thanks.
All right, so let's thank the speaker again.